To launch a fully reusable, multi-planetary spacecraft, you have to solve a physics problem that legacy rocket engines simply can't handle. You need an architecture capable of converting deep cryogenic propellants into an immense amount of thrust, while remaining durable enough to fly over and over again. When you look at the base of the Super Heavy booster, you're seeing 33 individual engines working in unison to lift the largest rocket ever built. But to understand how that lift is achieved, we have to look at the extreme precision required inside just one of them. Over the course of a single mission, these engines are exposed to drastic extremes. They ignite at sea level, shut down in the vacuum, execute cold starts in orbit, and rapidly reignite for an aggressive landing burn back on Earth. Raptor's specific internal architecture provides the mechanical baseline required to sustain Starship's reusable flight profile. Getting human beings to Mars and maintaining a permanent, sustainable presence there is, at its core, a matter of economics. Expanding our reach into space requires driving the cost per kilogram to orbit down significantly. Look at this 3D comparison of SpaceX's previous workhorse, the Merlin engine, next to the Raptor. The Merlin is reliable, but its maximum thrust output falls far short of what is required to lift Starship's unprecedented payload mass. To achieve the necessary price reduction for interplanetary transport, SpaceX abandoned decades of space-proven designs. They built an entirely new engine architecture from the ground up. This cross-section illustrates the solution they chose, the full-flow staged combustion cycle. This specific internal architecture is designed to maximize the impulse generated from every drop of propellant. Before reaching the main chamber, the super-chilled liquid methane and liquid oxygen pass through two separate preburners. One runs slightly fuel-rich and the other oxygen-rich, using a small amount of combustion to drive the turbines. Because 100% of the propellant flows through these turbines before entering the main combustion chamber, the engine achieves exceptionally high chamber pressures. That pressure translates directly into high-velocity exhaust exiting the bell nozzle. Engineering this cycle is incredibly difficult. Raptor is only the third full-flow engine ever developed, and the very first to successfully leave the test stand and fly. This extreme internal complexity provides the exact mechanical output needed to generate Starship's high thrust-to-weight ratio. Fueling that cycle required moving away from traditional kerosene or liquid hydrogen. Instead, the engines run on a super-chilled mixture of liquid methane and liquid oxygen, often referred to as methalox. Methane has a distinct physical advantage. It is fairly dense, meaning the propellant tanks stay at a manageable size for long-duration interplanetary trips without sacrificing the necessary thrust. It also burns exceptionally clean. Avoiding soot buildup, known as coking, inside the engine components is a strict requirement for reusing the vehicle rapidly without heavy, time-consuming maintenance. This chemical breakdown shows how carbon dioxide and water molecules can be combined to form methane and oxygen. This process allows future missions to manufacture their return propellant directly on the Martian surface, using its CO2-rich atmosphere and subterranean ice. The choice of methalox ties directly into the vehicle's two primary requirements: rapid turnaround here on Earth and the ability to refuel on another planet. Building a powerful engine is one step. Arranging enough of them to lift thousands of tons is another. The Raptor has to scale to fit within the massive 9-meter diameter footprint of the Super Heavy booster. This blueprint maps out the layout of Super Heavy's 33 engines. There is an outer ring of 20 non-gimbaling engines, a middle ring of 10 gimbaling engines, and 3 centrally located engines that also gimbal for precise steering. The second stage, Starship itself, uses a different configuration. It hosts 3 standard sea-level engines paired with 3 distinct vacuum-optimized engines. To maximize efficiency in the zero-pressure environment of space, the Raptor vacuum engine utilizes a significantly larger expansion nozzle. This makes the Raptor a modular platform, physically adaptable to both the brute force required to escape Earth's gravity and the high-efficiency demands of deep space travel. In flight, the engine's flexibility is tested almost immediately. As the vehicle hits max Q, the moment of peak aerodynamic stress, the engines must precisely throttle down to prevent the rocket from tearing itself apart. Shortly after, the system executes a hot staging sequence. Most of the booster engines cut off, while the second-stage Raptors simultaneously ignite to forcefully push the two vehicles apart. Once in orbit, the demands shift again. The engines must sit in the freezing microgravity environment of space and then execute reliable cold starts and in-space relights. Raw physical thrust gets the vehicle off the pad, but the advanced software control, precise throttling, and relight reliability ensure the mission actually succeeds. Returning Starship to Earth introduces the most extreme mechanical demand of the entire flight. To arrest its terminal velocity, the massive ship performs an aggressive flip and burn maneuver. This maneuver relies on a crucial hardware specification. The Raptor engine can gimbal up to 15 degrees on the Y and Z axes, allowing the flight computers to aggressively redirect the thrust vector in the fraction of a second. Getting this hardware to survive these forces repeatedly required SpaceX to iterate. Over time, they have relentlessly simplified the system, evolving from the complex plumbing of Raptor 1 to the highly streamlined Raptor 3. Raptor 3 eliminates the need for engine heat shields entirely and reduces the number of 3D printed parts to allow for mass manufacturability. Rather than adding heavy protective systems to solve the inherent fragility of the full-flow staged combustion design, SpaceX integrated and simplified the physical hardware to achieve true rapid reusability. The full-flow staged combustion cycle, the methalox propellants, the clustered layout, and the rapid restart capabilities are interconnected solutions to a rigid set of requirements. Without this exact, highly iterated engine architecture, Starship's goal of providing economical, multi-planetary transport remains physically impossible. Developing an engine to land a 5,000-ton rocket solves the problem of descent. Securing the vehicle at the pad requires the mechanical coordination of the launch tower.